So you need to make sure you have your calculator, your best friend, something to write on, and your eye clicker. Like I know I'm missing something here. So I know this weekend, you're going to want to say, oh, I just took an exam in, no, not this weekend. I'm like mixed up. So you have, next time I see you on Tuesday, you have exam 4, which is chapters 10, 9, and no, 8 and 9. Trying to keep track of everybody, 8 and 9. So when you're studying for the exam, but when is your final exam? On Friday. So don't forget, you need to be kind of working on that all the time right now. You're getting really close to that final exam. Okay. Like I don't want it to catch you by surprise because you won't have another weekend to study for the final exam. You understand what I'm saying? Yes.
Final like questions, like types of questions from our old text.
Similar types. Yeah, but not the same questions, but similar. But like, if you want practice, that exam practice on Moodle has all kind of practice questions. So don't forget to do your seating chart. And then we need to do some eye clicker. So let's go do eye clicker. I think it is this one. Yep. View full screen. Now, I'm going to tell you for this one, I want you to get out a sheet of paper because you're going to do a neutralization reaction and then you are going to pick the equation. But I don't want you to just pick the equation. I want you to not look at the answers until you write the equation and you write the answer. Okay, so get out a sheet of paper and draw the neutralization reaction of H2SO4 and KOH. I'm going to give you 2 minutes and 30 seconds. Please make sure your masks are covering your nose and your mouth. Put the chat up. Remember, 2 minutes and 30 seconds. So you still got time. Okay, so I'm going to give you until 3 minutes because everybody's taking a long time. But 3 minutes, I'm cutting it off. 3 minutes. Got about 10 seconds. So if you haven't guessed, make a guess. All right, turn and talk to the people around you. Make sure you click in for a second time. Click in for a second time. I'll close it at 45 seconds, so make sure you click in a second time. Okay, so what did we say? E is the correct answer. So what did you have to worry about with this? What are you making in a neutralization reaction? A salt and water. So where does your water come from? We have a hydroxyl here and a hydrogen here, right? What you should have had a red flag was saying that's two hydrogens. So that should have been a red flag for you, but you would have had to balance this equation. So what do you get that's left? You have a metal and a polyatomic ion, right? So if you have K, what's the charge on K? +1. My SO4, what's my charge? -2. So I had to be very careful because that would give me a 2 here and a 1 here. So I would get K2SO4. So you couldn't have these that didn't have the 2, right? That should have been a 4. But then what you should have noticed is that you had 2 potassiums. So you had to put a 2 here to balance the potassium, which also means you have 2 hydroxides, which means they match with these 2 hydrogens to give you 2 waters. Okay, good. All right, let's try another one. So it should have been E. I didn't say that. I think I said that. What are the products of the reaction? Now you don't have to balance anything. Just tell me what are the products of the reaction between hydrochloric HCl and NaHCO3. Try not to say the name. Okay, you're better off jotting things down. Okay, 10 seconds. Remember that the chat is only for when you're in the group. Okay, if you haven't already clicked in, please click in, make a guess. Make a guess. Okay, so turn and talk to the people around you. Now you can use the chat.
Yeah.
Forget 33, I'll go ahead and close it. So it looks like everybody's done talking about it over here. There we go. That's everybody, all right? Okay. So when you were doing this, right, what do you notice? I can make NaCl, and what else can I make? I need water, so that's H, right? That's H2, and then what do I need? I need 1 oxygen. What's left? What's really left, I no longer have CO3, I now have CO2, right? I have CO2. So I'm making water, a salt, and carbon dioxide, right? So this is what kind of a reaction? This is a neutralization reaction, right? Okay, pretty good. All right, now this is what we did in class so much Tuesday. I always want to say yesterday. So how does the addition of NH4 plus, and look, I highlighted it for you, NH4 plus affect the equilibrium of the reaction shown? So you tell me what happens when we add ammonium. So remember, you can jot down, we do this, the reaction does that, and the product is. Okay, 10 seconds. Everybody needs to click in. Oh my God, we had 33 people before. Click in. Okay. So turn and talk, and then click in again.
Yeah.
Okay, 5 seconds. Okay, so what you should have automatically done is crossed off C and D, right? Because you're doing something, you're stressing this reaction. So what did we do to the reaction? We increased a reactant or a product? A reactant. What did the reaction do? It decreased it, did the opposite. So what kind of a shift does that make this? If we want to get rid of reactants, we need to go towards the product. So what kind of a shift is that? A right shift. So what did we say? B, good. Very good, awesome. Yay. All right. So let's go back to our problems. Go back to our problems. I think we were right about here. Right, and the last thing we were doing is we were looking at a reaction and we were saying, okay, this is an acid, it turns into a conjugate base. Here's a base, it turns into a conjugate acid, right? Okay, so now we're going to do the same thing, except we're only given one little piece of information. So if we look at this and we say, write the formula and name of the conjugate base formed from each of the following acids. So what this is telling me is all of these are acids. If they are an acid, what will they do? Accept a hydrogen ion or donate one? What? Donate. That's one of those things you need to donate or accept. What are we going to do? Donate or accept? You need to know. So acids donate, bases what? Accept. So if we have this acid HCO3 and it donates a hydrogen ion, that means you take the formula and then you take away a hydrogen. So we have HCO3 minus. So we're going to do this and we're going to remove not just a hydrogen, but we're going to remove a hydrogen ion. So did you see what I did when I said ion? I wrote a plus because that's a +1. So then what does that turn into if I take away the hydrogen? It turns into just CO3, but what else has to change? The charge has to change. So if this was negative and we lose a positive charge, what charge do we become? Yeah? What do we call this? Do you have to remember? Go to your polyatomic ion, right? It's multiple atoms and those atoms are charged. So what are we going to call it? Carbonate. Okay, so I'm going to erase some of this to make room. I'm not going to erase the answer. I'm just going to erase some of this because this was A, right? B in blue. So water, when it picks up a proton, right, it becomes H3O plus. So what happens if we have H3O plus and it donates a hydrogen? Becomes simply H2O. What do we call it? We call it water. What's something else you could call it that's more scientific? Love it. Dihydrogen monoxide. Okay, HPO4 2 minus. We're going to donate a hydrogen. We're going to get rid of a hydrogen ion. What do we get? PO4. Now I'm going to get rid of one, so I'm going to become more negative. So I should be 3 minus. So what is my name? Phosphate. Okay. D, HNO2. I'm going to donate a hydrogen. Just get rid of the hydrogen. I end up with NO2, but I have to worry about charge. So if I was neutral to start with, and I lose a positive, what am I? Negative. So now I have a negative on there. Go look on your polyatomic ion table. What am I? That's right. Okay. Now we got to change gears. Now we're told we have what? We have bases. So all of these are bases. Bases will do what? Hydrogen ions. Okay. So we have SO4 2 minus. So what I need to do is just add an H plus. What do I get? H, SO4. I'm going to add a positive. Minus. Now, we're making a conjugate acid. Sometimes when you make a conjugate acid, when you're naming it, you don't necessarily name it something acid, especially if it's charged. If we're charged and we have more than one atom, where do I go to find a name? Where? Polyatomic ion table. So go to your polyatomic ion table. What is HSO4 minus? Hydrogen sulfate. Or not bi. Right? Okay, CN minus. Add a hydrogen ion to it. What do you get? HCN, and it's not charged. When you go in the polyatomic ion table, what is the name of CN minus? Cyanide. What does cyanide end in? IDE. All the other acids that end in IDE, what do we name them? Like if I had this, how would I name this acid right here? Hydro, right? Hydro, and then we name the element chloric acid, right? Because it's the chloride ion. So if I have cyanide, cyanide's weird. It ends in IDE, but you find it on the polyatomic ion table. So we have, if it ends in IDE, we have to do this naming scheme. So what should I call it? Hydro cyanic acid. Okay. OH minus, what happens when we do that? H2O, what do you call it? Water or dihydrogen monoxide, same thing. Okay, ClO2 minus, the chlorite ion. Call it HClO2. What's my charge? No charge. So we don't name it as a polyatomic ion. What do we name it as? An acid. So remember, I went to chemistry class and I got itis. So it ends in ITE, so it needs to turn into OUS. So it should be OUS, chlorous acid. So why do we name some of them with acid and some of them not? The ones that we named as acids, are they charged? The ones that we named as polyatomic ions, were they charged? Yes. So you see the difference? Yeah. If you know what you're looking for, it's not too bad. All right, complete the following reactions and identify the conjugate acid-base pairs if the named reactant acts as a what? As a base. So the named reactant is a base. In A, what is the named reactant? Pyruvate. So this right here is pyruvate. When you eat sugar, right, glucose goes through glycolysis, and the end product of glycolysis is pyruvate. So it's a product of glucose metabolism. So if it acts as a base, by definition, what is it going to do? Accept a hydrogen ion. Okay, so if this is the base, what is water? An acid. So if water is an acid, what is water going to do? Donate. So if water donates, what's left? Just OH minus. So my OH minus, where did that hydrogen go that was attached to the water? And it's aqueous. Where did it go? It went to my pyruvate. So where in the world do I put the hydrogen on that pyruvate? So you go and look for a negative charge. Where do you see a negative charge? On that very last oxygen. Stick your hydrogen in place of the negative charge. So rewrite the whole thing, CH3, C double bond into an O, C, O, O, H. Okay, now we have to identify the conjugate acid base pairs. So if pyruvate is our base, what is the thing in black that I just drew? This is the conjugate acid. If water is acting as the acid, what is this OH minus acting as? Conjugate base. And I didn't put this, but it is aqueous. Not too bad, right? Okay. Dihydrogen phosphate, a component in cell buffering, which we're going to talk about later today. H2PO4 minus. What is this acting as? A base. This is our base. So H2O is acting as an acid. So it's very easy for me to draw the conjugate base of water, which is OH minus. I'm going to make it aqueous. Now I need to do my base. My base, H2PO4 minus. If I want to turn it into a conjugate acid, what do I do? I'm going to accept a hydrogen ion and I'll be H3PO4. What's my charge? No charge, and it is aqueous. What do you think? Got it? Try one more. HCO3 minus, which is bicarbonate, is acting as a what? Acting as a base. That's just what it told us in the question. So water must be acting as a acid. Okay, so let's do water. When water turns into the conjugate base, I know I get OH minus. My base is going to pick up a hydrogen. So I'm going to go from having one hydrogen to having two. My CO3 negative now becomes neutral, no charge, and it is aqueous. And we call this the conjugate acid. Now, before we go on, look at C here and look at C here. If I can get them both on the screen at the same time. Okay, this is bicarbonate, right? What is this? Bicarbonate. Bicarbonate here is acting as a, bicarbonate is acting here as a, what? If I look here, dihydrogen phosphate is acting as a, here dihydrogen phosphate's acting as a, what? So there are some molecules that are really, really cool that can act, they can act as either an acid or a base, right? These things that are really, really cool are called amphoteric, A-M-P-H-O-T-E-R, amphoteric. They're amphoteric molecules. So a lot of times when you have buffers, you have substances that are amphoteric because you have to take into account an acid challenge to the system or a basic challenge to the system. And we'll talk about that in just a little bit. Okay, so now we're going to talk about pH. Now that you kind of understand acids and bases, we're going to talk about pH. Basically, if you have, if you have a high pH, what does a high pH tell you? You have a pH that is greater than 7. What are you? Basic. So this is a high pH, right? That's what we kind of said. If you have a pH that is equal to 7, what are you? Neutral. If you have a pH that is low, means lower than 7, you are acidic. Okay. Are we neutral? You and I, physiologically, are we neutral? Not quite. We're close. We're very close. What is this? Is super important. This is super important. What is physiological pH? That is correct. 7.35, 7.45. So what are we really? A little bit, we're a little bit basic, okay? So body pH is not neutral, it's not. We operate slightly above a neutral pH. So when we talk about pH, what is pH? Why do we say the word, why do we say the letters pH? What does that H stand for? It stands for hydrogen ion concentration, right? So the definition of pH is the negative log of the concentration of the hydronium ion, which is the same thing as H+. That's why we call it pH. The P stands for negative log, right? P is always equal to the negative log of whatever. So that's where we get our formula. The negative log of some concentration tells us the pH. The reason that we invented the pH scale is because people had a really hard time looking at negative exponents, huge negative exponents. It just didn't make sense. And so we converted it to a pH scale that's much easier to visually see and make decisions about. So when we look at solutions, say for example, soda, and I tell you it's a pH 3.2, can you tell me if that is acidic or basic? Sure, it's acidic. Shampoo with a pH of 5.7. That's also acidic. Laundry detergent, pH 9.4. Basic. Rain, pH 5.8. Acidic. That was really quick and easy, right? Now, I look at these numbers. Can you tell me real quick, is A acidic or basic? So you really had to think about it, right? Takes you more time to think about it. So my suggestion to you is don't try to analyze it. Convert it to pH. So if I wanted to find the pH, right? pH is equal to the negative log concentration of H3O plus, right? So for A, my pH is equal to the negative log of 5.6 times 10 to the minus 10. So if we do this, I'm going to put on this side, I'm going to put the calculator. On this side, I'm going to put the screen. Okay. All right. I have to zoom. Well, I'm actually going to leave it. Most people have this kind of a calculator. Some people probably have one of these. Yes, no, not too many. Okay, so I'm going to do it with this one. And if you have a different calculator and you need help, stay at the end and I'll help you. Okay, so some of the buttons that you really need, see if we turn this on. You need to know where log is. So do you see log is right under second? You're going to need that. Now, you see the little blue numbers above log? What does it say? 10 to the x. So how do I get 10 to the x? Press second, right? So what that's telling you, the reason they set this up on the calculator this way is that 10 to the x is the opposite of log. It's the inverse. That's why calculators are built this way, right? So if we do this, I'm going to say the negative log. If you look at a calculator, you have two things that look like negative signs, right? This blue one is a minus. The white one is really negative. So anytime you hear negative, this is the one you're going to press, right? So I'm doing the negative log. So do I press the blue one? No, I'm going to do negative, and then I'm going to come up here and I'm going to press log, right? So negative log, I'm going to type in 5.6. Now, I want it to say times 10 to the negative 10. There are a couple of different ways you can do it on your calculator. What I do is I do second, and then you see this x to the negative 1. And you see the EE. Because I hit second, it's going to put an E, which is the same thing as times 10 to the. And I'm putting a negative 10. So a negative 10, I have to press negative down here. 10. Now, can I hit enter? No, what do I have to do? Close my parentheses and hit enter. And I get 9.25 pH is equal to 9.25, right? Okay, I'm going to teach you a little something. Do you see on my calculator where it says 9.25 times 10 to the 0? You see that? That's telling me that my calculator is in scientific. So if you look at your calculator, you see where it says degree? And up at the top, it says science engineering. So if you press second and press that button, your calculator is probably either in flow or scientific. If it's in flow, it just shows it without the times 10 to the. But if you put it in scientific, it gives you it in scientific, your answer in scientific notation all the time. Pretty neat, huh? Okay, so make sure that you're aware of whichever one your calculator is in. Okay, all right, so I'll put it back on flow just so that's probably it. Okay, the other thing that you're going to notice is, do you see how this is two significant figures? The number of significant figures tells you how many digits past the decimal your pH needs to be. Makes no sense, right? It does, but you don't have to worry about it. I'm in the habit of always doing that. So it's okay. You're going to have a multiple choice exam. And I promise not to give you a significant figure question with pH. So just realize if I'm writing the wrong number of sig figs, it's not the wrong number of sig figs. It's because the rules are different when you're using logs. Okay. All right, so B, type in B. I'll do B on the calculator and then I'll switch. So I'm doing the negative, right? The white negative down here, negative log, and this is 6.2, and then I'm going to go second EE to the negative 8, close parentheses, hit enter. 7.2. So this one is 7.2, right? Yes? Did y'all get this? If you're not getting it, now's the time to say it. Okay, what do you get for C? Do it for C. Let me switch back. The negative log of 5 times 10 to the minus 2 is 1.3. Okay, in D, the negative log of 1.8 times 10 to the negative 6 is 5.74. Should be 7.2. Okay, now you're looking at these numbers. Can you easily tell me if it's an acid or a base? Absolutely. So tell me for A, because A is really down here. Is A an acid or a base? Base. Is B an acid or a base? Base. C, acid. D. Wasn't that so easy? I think that's the easiest way to do it. Okay. All right. So the next question said calculate pH of each of the solutions in problem 9.44. We did it. We're done. We did it. Right? Okay. Now, oh my gosh, this is weird. Calculate the hydrogen ion concentration for each of the following measurements of pH. What's the formula for pH? Okay, so now in this case, I'm given pH and I have to solve for the H3O plus. So what do? I move my negative sign over, right? Because I can divide by -1, divide by -1, that gives me negative pH is equal to the log of H3O plus. How do I get rid of log? I do the inverse of the log. What is the inverse of the log? I showed you on the calculator, on the button above log, what is the inverse? 10 raised to whatever. So to get rid of log, I raise that side of the equation to 10 to the, and it cancels it out. But I got to do that same thing to the other side. So I get 10 to the negative pH is equal to the hydrogen ion concentration. Do you have to memorize that? No, you don't, right? Because what do I do on your equation sheet? I gave it to you. I gave you that exact equation, okay? So make sure you can find it on your best friend. Okay, so now can I erase this stuff down? Okay, so now I'm gonna erase this. So we don't really need that because you already have that equation. I just think it's important for y'all to see where it comes from. Okay, so now we have a pH of 12.1. So I'm going to say 10 to the negative pH is equal to concentration of H3O plus. So I go 10 to the negative 12.10 is equal to H3O plus. So I'm going to switch over and show you my calculator. Show you how to do it. Okay. All right. So now I'm going to do 10 to the. So you go second and you press that log button and it gives you 10 raised to the and it opens parentheses. So now it is a negative 12.10, not a minus. So which one are we going to use? The white one or the blue one? The white one. Negative 12.10. Am I good? Close parentheses, hit enter. Now, what if you get something that shows you 0.00000, so on and so on, 7942. What do you have to do? Put it into scientific notation. Okay, so just be aware of that. But this one, we're given, it is 7.9, 2 places, 2 sig figs, times 10 to the negative 13. Yeah. Right now, I'm missing one thing. Missing units. So when I look at concentration, what unit am I working on in concentration? The big M. What is the big M? Molarity, moles per liter. So I'm always going to put times 10 to the negative 13 molar. That's how we say it. Okay. So the same thing we do for B, I would do second log, and I would do negative 5.5, close parentheses. Oh my gosh, I'm gonna have to count that, right? Or if you know how to use your calculator, what can I do? I can swap and I can go second degree, switch to scientific. Oh, isn't that magical? What do I get? 3.1, one place past the decimal, 1 sig fig, so it should be 3 times 10 to the what? Negative 6 molar. You don't have to. You don't have to. It's going to be multiple choice, and I don't make any of the answer choices different just by significant figures. I think that's mean. Unless I'm testing you on significant figures, and I'm not doing that with logs. So no big deal. Okay, gastric juice. Can I take this one down and put the other one back up? Okay. All right, gastric juice. I want to do 10 raised to the negative 2. What do I get? Just 1, and this is really 1.0 times 10 to the what? Negative 2. Right? That's C. C, not A. D is 10 to the negative 8.3. What do I get? I got 5 times 10 to the negative 9. Yeah. Pretty good. If you have calculator issues, please stay after class and let me help you. Okay. If you're not getting this with the calculator, do not wait. Okay. All right. So now, you remember how we talked about Ka, right? That was. Remember how we talked about Ka? What is Ka? It's the equilibrium constant for an acid. So how do I write the equilibrium expression? I always put my products over my reactants. So a typical expression for an acid would be HX yields, and you would go back and forth, right? H plus plus X minus, right? Because that acid's losing the hydrogen. Y'all agree with that? So here are my products. Here are my reactants. Now, just like we said, it's really hard to understand concentration of hydrogen ions. So we did the negative log of them. The same thing is true about K. I know that y'all thought that, you know, you're like, oh my God, I'm looking at these things with exponents and I have no idea what they mean, right? Everybody felt that way. So what they did was they said, well, let's do the same thing that we did for pH, and we're going to get a pKa. Okay, so pKa is equal to the negative log of the K, or the Ka, really. So we can look at the pKa or the Ka values and make predictions about our acids. So I want you to look at that strongest acid on this weak acid chart, the hydrogen sulfate ion, HSO4 minus. It has a pKa of 2. That is really close to 1. So what is that telling me about my reaction? If I compare hydrogen sulfate ion and let's say water, right? Which one is making more? And I did this, why did I do this? Reactants and products. Why did I do this? Y'all, seriously. So which one is making more product? Hydrogen sulfate ion or water? If you have something that is a strong or a stronger acid, more hydrogen ions dissociate. Right, now remember that? Okay, so if they dissociate, are we making more reactants or are we making more products? You make more products, right? So then this number, the numerator, is going to be bigger. So tell me about that Ka value. Ka is going to get bigger as we get stronger. So down here we have a small Ka. Up here we have a larger Ka, right? So more products, larger Ka. So how does that translate to pKa? Well, look at the comparison. Here's my weakest acid possible. It is at pKa of 14. If I look at hydrogen sulfate ion, I have a pKa value of 2. So in this case, the stronger the acid, the closer pKa to 1. So the closer your pKa value is to 1, the stronger that weak acid is. Please make sure those masks are covering noses and mouths. So our pKa value, the closer it gets to 1, the stronger the acid is. Okay. Now, do you have to really memorize that? No, because you're going to get the table. You just don't get this arrow. Okay. So if I come down here and I'm given different acids, can you determine which one is stronger, which one is dissociating more? Absolutely. All you have to do is look at their pKa values and which one is closer to 1 is the stronger acid. So HCl and HCN, are they both on the table? HCl is not on the table. Why is HCl not on the table? It's already it's a strong acid. It's not a weak acid. That table is just weak acids. So what's stronger, a strong acid or a weak acid? A strong acid, HCl. We don't even have to look anything up. B, acetic acid and ammonium ion. What is the pKa value for acetic acid? 4.76. What is it for the ammonium ion? So which one is closer to 1? Acetic acid. Carbonic acid or bicarbonate ion. The carbonic ion is what? 6.35. Bicarbonate is 10.32. So carbonic acid is closer to 1. Mass over noses, please. Ammonium ion or hydrogen phosphate ion. So ammonium is what? Hydrogen phosphate, 12.0. So which one? Ammonium. So we can use these pKa values to predict what will happen at certain pHs. And this gets super important for drugs and how drugs interact in our bodies. So here are a couple of two different drugs, niacin and acetyl salicylic acid. If I look at these, which one is going to be the stronger acid and why? Acetyl salicylic acid is going to be stronger. Why? pKa value is closer to 1. Okay, pretty cool. Now let's apply that. Oh, I'm going to talk about, I just need some room. So I'm going to write down here and then we'll go on to the next one. I just need some space. So drugs are really, really, really important in their design, drug design. Because we really have two goals for our drugs. We want our drugs to be, number one, soluble. S-O-L, soluble. What do we want it to be soluble in? In the bloodstream, what is the major, the universal solvent? Water, right? So your bloodstream is mostly water, really. So we want it to be soluble in water because we want it to be soluble in your bloodstream. We also want to be able to give it to you so you can orally take it and it'll dissolve in your stomach acid, which is also water based, right? We want to be able to put it into a syringe and put it into an IV. Therefore, it must be soluble, right? So all of this is really important for drug design. How do we make sure something is soluble in water? What is water? It's polar. You get nothing else from this class. You're going to know that water is polar. So water is polar. So our rule for solubility is like dissolves like. If it's polar, will it dissolve in water? Yes. Could you think of a stronger interaction which would make something even more soluble? What's stronger than just a polar interaction? What about a ion dipole interaction? That's really good, right? What do we need for something to be soluble in water and have an ion dipole interaction? We need it to be charged. So drugs are charged. That's great. Awesome. It's soluble, super soluble. There's a problem. It's a drug. It needs to get into a cell. Do charged things go across the cell membrane? No, they do not. So number two, we want it to cross the cell membrane. What must it be to cross the cell membrane? Neutral. What in the world am I going to do? I need my drug to be two things at once. How can I go from a charged to an uncharged? We did this today. We went from an acid form to a conjugate base. Well, not necessarily neutralization, but just converting that drug from the acid form to the conjugate base form. You can go from a charged form to a neutral or a neutral to a charged, either way, right? So all of this happens when you go from an acid form to the conjugate base. You could have something that was charged going to something neutral, or you could have something neutral then becoming charged. And all I have to do is change the pH, and those hydrogens start popping off when I want them to, which is really awesome in drug design, right? So have you ever seen the drugs, like the sinus congestion drugs? They say whatever the drug name, HCl. Never seen that? Look at the no-name brands. Don't look at like Sudafed, right? Or look at Sudafed, but then look at the actual drug name. You'll see that lots of them are like that. That's because we're utilizing the system. Isn't that cool? Okay, so let's apply that information, right? Okay, so what I can do, I just said this, is that I can change the pH and therefore convert my acid to a conjugate base, right? So if my pH is less than my pKa, right? What does that mean? Well, that means that I'm not going to lose my hydrogens, right? Because what does pKa tell us? What is pKa? Negative log of the Ka. What is K? Products over reactants. So if I have an acid, I'm going to really favor my reactants, right? So all this is doing is it's telling me which way the equation is going to shift depending on the pH. If the pH is smaller than the pKa, I'm going to what? Keep my hydrogen. If my pH is greater than my pKa, what's going to happen? I'm going to lose my hydrogen and I'm going to be a conjugate base, right? If you keep your hydrogen, you're an acid. If you lose your hydrogen, you're a conjugate base. So now, what happens when my pH is exactly the same as my pKa? I'm going to have 1/2 in the acid form. I'm going to have 1/2 of my molecules in the conjugate base form. So half of them will have the hydrogen and half of them won't. Isn't this so cool? Okay, so let's kind of apply this. So this is an example medication. It's an anticonvulsant of valproic acid. It is shown as an acid below. Okay, the pKa for the acid is 4.8. A, which form is charged? Acid, conjugate base, or both? Stop before you answer. Okay, look at the molecule. Which form is the molecule? What am I looking at? Acid or conjugate base? Shown as an acid below. So this is an acid. Now, what happens if I want to turn it into the conjugate base? I'm going to lose the hydrogen. Which hydrogen do I lose? This bad boy right there. So all I have to do to draw this is to draw exactly the same thing. Don't put a hydrogen, and then what? It's negative because I lost a positively charged hydrogen ion. Now go and answer A. Which form is charged? Acid, conjugate base, or both? So easy now that you understand conjugate bases, right? Okay. Which form will predominate in the first part of the small intestine, the jejunum, where the pH is between 6 and 7? What's the pH? Somewhere between 6 and 7. What's my pKa? Always compare pH to pKa. Which one is bigger? pH. So I'm going to go up to my table. What happens when my pH is greater than my pKa? I lose the hydrogen and I have conjugate base. So we have conjugate base. Okay. C, which form, acid or conjugate base, will be able to more easily diffuse through a cell membrane? More easily diffuse. What do I want? Neutral. So which form will diffuse? Isn't that cool? So all you have to do is be in different parts of the body, and different parts of the body have different pHs, and the drug will behave differently. That's why the drugs are in a solution of hydrochloric acid. It makes it a very what? Acidic environment. Okay. All right. Consider the neurotransmitter dopamine, which has a pKa value of 8.9. Will the acid or the conjugate base predominate at the following pH values? Okay. So if I have a pH, I'm going to always compare my pH to my pKa. So first I have 7.45, then I go up to 8.9, and then I go up to 13.40. What's my pKa? 8.9. Does pKa ever change? No, it's based on a constant. So it's always going to be 8.9. Does not matter what pH your solution is, your pKa will never, ever, ever change. So in the first one, at pH 4.5, which one's higher, pH or pKa? pKa. What happens in the second situation? Equal, and the third, pH is higher. So if pH is lower than pKa, like right here, tell me about what's predominating. The what? The acid form. That's correct. Acid predominates. How about my second situation? Ooh. You have half and half. Equal, however you want to say that, right? Now, how about the last situation? The conjugate base predominates. At each pH, is that form charged or uncharged? If this is dopamine, and dopamine here is listed as the acid form, what happens? The only thing that's important is this NH3. None of the rest of this changes. So what happens to this NH3 when we go from the acid form to the conjugate base? I now have NH2. What about this positive sign? It goes away. So my conjugate base is what? Neutral. So at each pH, is that form charged or uncharged? So here the conjugate base is uncharged. Here the acid form is charged. And then here it's really half and half, still half and half. Yeah? Okay, you don't have to do C. Mm-hmm. So I looked last class, and I don't think I have it on the best friend. I'll add it to our best friend. I'll add it. It's not on there. I'll add it. Okay. So now we're going to talk about another drug type. Another drug type are anesthetics. So all anesthetics, when we talk about them in general, right? This drug type is all anesthetics are charged in the acid form, right? And the reason that they're charged is they have that amine group, right? So if you have 4 different things attached to it, you're positively charged. So this nitrogen has 4 different things, one of them being a hydrogen. This hydrogen can then deprotonate, it can come off, and then we would have 3 things attached to it, right? But because we have 4, this nitrogen is positively charged. So this is the acid form. This is always going to be the conjugate base form. So that's for all anesthetics. So when you design these anesthetics, right, you want to worry about the pKa value of those groups because they're going to determine how effective the drug is in treating pain, right, in doing its job. So we're looking at these 2 different anesthetics. They all anesthetics end in cane. Do you see that? So I don't even pronounce these, but anyway, we have 2 different ones. One of them has a pKa of 7.6. The other has a pKa of 8.1. Wrote right over it. pKa of 8.1. The question is, which of these 2 is going to have more of the uncharged form? Because the more of the uncharged form we have at that physiological pH, the more quickly it's going to enter the cell, the more quickly it's going to do its job and relieve the pain, right? So what do you need to do to get to the neutral form? Lose the hydrogen, lose the hydrogen. When do we lose the hydrogen? When your pH what do I have to go back a slide? We lose it when your pH is greater than the pKa. So the closer your pKa value is to physiological pH, the more it's going to do. Oh, I went the wrong way. Okay, so the closer your drug's pKa value is to physiological pH, so the closer the pKa value is to physiological pH, the more of it is in the conjugate base form, which is neutral, which will pass through the membrane, right? So which one has a pH closer to physiological pH? The one with 7.6. That's pretty easy, right? As long as you know that, you're good. Okay, last one. Last one, yay. All right. There are lots of places in our bodies where we have to keep a particular pH. We have to maintain pH values. Things, proteins, DNA, all the kind of stuff, everything that's in your bodies work at an optimal pH. Sometimes it's physiological, right? But what about the stomach? Are we at physiological pH in the stomach? Actually, no, not really, right? What's in your stomach? Hydrochloric acid, right? So you have a super low pH in your stomach, but you actually have enzymes like trypsin that work and they're found in your stomach. Isn't that kind of crazy? But the whole point is that you need a particular pH and you need to stay at that pH. So how can you keep the body systems at a particular pH? You're going to use what's called a buffer. A buffer is always going to be a weak acid and the conjugate base, or a weak base and its conjugate acid. Because basically what you're doing is you're saying, I have a little bit of base and a little bit of acid. So if I get challenged by something very acidic, my base can soak it up. If I get challenged by something very basic, my acid can kind of soak it up, right? So you convert strong acids and bases to weak acids and bases, and that's a much smaller change in pH. So that's the whole point of a buffer, is to maintain a particular pH inside the body. So this is really important when we talk especially about blood pH. So I don't really like how this textbook question does it, right? It says a person who overdoses on antacids may neutralize too much stomach acid. So this antacid is acting as a what? If it neutralizes an acid, it's acting as a base. So which causes an imbalance in the bicarbonate equilibrium in the blood. And it gives you this equation. This equation is true, but it's missing something. So I want to fix it. So we know that most of our blood, right, is liquid. What liquid is it? Universal solvent, water. You undergo cellular respiration, you make what? Carbon dioxide gas, right? You inhale oxygen, you exhale carbon dioxide. But carbon dioxide actually dissolves inside of your bloodstream. And when it does that, what you're going to form is you're going to form carbonic acid, H2CO3. This is, I'm going to do this, carbonic, and it's an acid, right? Okay, and you also have water, right? You have water because you're in the bloodstream. Now, what happens to that carbonic acid? that carbonic acid is actually going to turn into, right? You have an acid and a conjugate base. What's your conjugate base for carbonic acid? If I go from an acid, I'm going to donate a hydrogen. I'm going to have one less hydrogen, right? So instead of H2, I only have H1 hydrogen and then CO3 minus, right? And then where did that hydrogen go? Well, water picked it up. So it's H3O plus, right? So technically what I've written is actually what happens. They just kind of gloss over that. So got to think about what happens when somebody takes too much of an antacid. Well, it's going to soak up all of the acid in the stomach, so you'll neutralize the stomach acid. But then that base, that antacid that they took, it's really a base, will actually enter the bloodstream. So that base is going to react with what? If I have this base, and I have basically this going on in the bloodstream, what's it going to react with? Bases react with, not bases. They react with acids, right? This is a base. It's acting as a base. This is a conjugate acid, right? So it's going to, the base is going to go in and neutralize your blood. So how does blood pH change when this occurs? Well, it's going to start dropping. It's going to start, I don't want to say dropping. It's going to start changing your pH, right? How is it going to change your pH? You're going to remove what? This base or this antacid, ANTACIDS. Woo. The base is the antacid. So what's the base going to do? It's going to remove, what does it react with? H3O plus. This is what gives you really low or really high pHs, right? So if we take away H3O plus, what's going to happen? pH will do what? Go up or go down? Will you become more basic or will you become more acidic? You become more basic. So what will happen to your pH? Up, more basic, right? It's a base. You become more basic. Okay. In which direction will the bicarbonate equilibrium shift when you have an Alka-Seltzer overdose? So we have more base. We are depleting that H3O plus. Which way is it going to shift? It's going to shift to the left. It's going to shift to the left. Yeah. Okay. And when you were reading in the textbook, what is this condition called? And I talked about it in the lecture too. Right? If you're basic, another way to say basic is alkaline. Have you heard that before? So they call it alkalosis. 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 Instead of acidosis, right? If you have too much acid, you're acidotic. If you don't have enough, you're alkalotic. Sounds crazy, doesn't it? Okay. So to treat a severe form of this condition, patients are administered NH4Cl, which acts as a weak acid. So they overdosed on base. So what's the treatment? Give them acid, give them an acid. So how does it restore the equilibrium? Well, I just gave them an acid. So what am I increasing? The thing that controls acid, H3O plus, right? So in which direction will the bicarbonate equilibrium shift as we treat the patient? It's going to go right. It goes in the opposite direction that you went before, right? So if when they're becoming alkalotic, they go left. When we treat them, they go right. Okay. study for the exam, but also you need to be working on studying for the final. If you have any calculator questions, if you need anything, please ask. Don't forget to do the extra quiz, right? The 20-point extra quiz. And if you have any questions, please let me know. Okay, anybody on Zoom have any questions? Okay, I'm gonna go ahead and end the Zoom.